part of it. 1 second. Okay, so we'll begin up with our fourth module. Our fourth module is about the artificial neural networks. There are two other concepts as well involved into it. The first is about the support vector machines, an extension to the logistic or the linear regression. We have one, which is the support vector machines. We'll be looking ahead at this. And you have some clustering methodologies, okay? One among them is the k-means clustering and the adaptive hierarchical clustering. So we will be looking at this along with our artificial neural networks. In artificial neural networks, you will be looking at the introduction, the neural network representation, the appropriate problems has been associated with it, or the appropriate problems that ANN solves, okay? And you have the basic model, the basic unit of ANN, which is a perceptron, the backpropagation algorithm, and introduction to deep neural networks. Okay, so this is going to comprise the entire, this completely forms your fourth module, which is with respect to the support vectors, ANN, and the clustering. Okay, so this forms your module 4. So to start with, okay, today we'll go ahead with support vector missions. Okay, as I told, it is an extension with respect to logistic regression and linear regression. Okay, so in machine learning, basically, I hope you would have listened to the term called as SVM, support vector missions. Have you? Any one of you? You know about support vector missions? Since you have heard about the term SVM classifiers, okay, let's go ahead and see what is SVM classifiers and how are we going to deal with this? How is it going to help us classifying our given problem statement or with respect to the data points? Okay, so in machine learning, SVM is basically a supervised learning model which is associated with a learning algorithm. It has a learning strategy. Okay, so that analyzes the data which is used for classification and the regression analysis. So it is used both for classification as well as regression analysis. Okay, so we already know, we have seen logistic regression and linear regression. Okay, logistic regression, like basically regression, is a statistical process for estimating the relationship among variables. Okay, outline of SVM. Here comes the important part. Okay, what does it has? Okay, what an SVM has? Okay, so now what I'm going to do here is I have certain data points. Okay, so these data points, I'm going to cluster it with respect to positive and negative. This is what I'm doing it. Okay, but let us see how SVM also does it in the next steps. Okay, this is the block diagram I'm just telling you. The main differences of SVM with logistic regression or linear regression is that, see, even logistic regression or linear regression, we're going to draw a line, right, to classify them into two different categories. We used to draw a line. Okay, when we're drawing a line, we used to come up with the best solution, right? Remember your linear regression line, y is equal to mx plus c. We had the x and y value given. Using the x mean and the y mean, we calculated the m and c value. Once we got the m and c value, we substituted x value into it to get the corresponding y value, and we drew a line, right? So now what I'll do is I've been trying out with multiple options. Now I've come up with one best fit solution. That is what we were doing in the linear regression or the logistic regression. But here with SVM, it's a similar methodology of using the linear or logistic regression with an additional point of creating support vectors. What are these support vectors? Now I have a hyperplane. Now what I'll do is the line that I drew, y is equal to mx plus c, I will consider this to be as a hyperplane. So this is my hyperplane. Okay, so this is my hyperplane now. I've drawn this hyperplane. Okay, so with this hyperplane, what I'm going to do here is identifying the support vectors. Support vectors is nothing but you identify a data point. Okay, identify a data point that is closest to this hyperplane. Identify a data point that is closest to the hyperplane and create a similar parallel plane to the hyperplane. So this is my hyperplane. I'm going to identify the closest point. Suppose I'll consider these two are the closest points to the hyperplane. Using that closest point, draw a parallel hyperplane. So you will have a parallel plane to the hyperplane. A similar, draw a parallel plane to the hyperplane. Wherever I'm going to identify these points, right, okay, that is going to lie on this particular parallel plane, they form my support vectors. These are my support vectors. Okay, these are my support vectors, and the remaining other are as usual in the data points. Okay, I'm going to identify, as I told you, the point that is closest to the hyperplane. See here, this is closest to the hyperplane, but this has some larger value with respect to the hyperplane. So I'm going to identify the closest value to the hyperplane and draw a plane that connects all of these support vectors, the data points. So the distance between these two forms my margin. Okay, it's like I have a plane that I'm created. Along with that, I'll create two more hyperplanes that is connecting to most of my support vectors. Okay, so now I'll have three parallel lines like this. So these parallel lines, the distance between those two parallel lines to the middle line, they form the margins. So this is the background of support vectors. So you'll have margin. Maximum the margin, the more your classification problem is. Like it best fits the solution, the maximum. So SVM normally, whenever you have a given data point, whenever it starts creating these hyperplanes and these parallel planes, it will try to see that it has the maximum marginal distance. You're getting it? Maximum marginal distance. This distance, whatever I'm talking about, should be more. This will be the positive D because it's the positive side of it. This will be the negative D minus. So this total distance, okay, it's going to be my margin. And I know about. So there are three main things that we came to know over here. First one is the separating hyperplane, the line that I'm drawing. Along with that, second one is the margins based on the support vectors. So three important things that we have read through here. Now, okay, why do they tell I have to have a margin more? Let me give you one example over here. See, rather than drawing a hyperplane like this, I will draw a hyperplane like this. I will draw a hyperplane like this. If it was a linear regression line or a logistic regression line, for sure this would have accepted, right? Is there any issue with this? With respect to linear or
Yeah,
logistic regression, we would have surely gone through. I have created a line that segregates two things, so I'm fine with it. But when I told it is with respect to SVM, SVM has the characteristics of support vectors as well as margins. So you just take an example here. Now, what will be the distance between this? So this is going to be the distance, right? This is one of my support vector. I'm going to identify the shortest distance between the hyperplanes. So this will be here, 1 point. Okay, the second point within this, probably this is the only shortest distance that I have. So I'll consider these two shortest distance. So I have this distance and this distance. Looking at these distances, I have to calculate another parallel plane. Okay, now I'm going to draw a parallel plane. Please do not mind for my drawing. I've created my parallel planes. You can see what is the marginal distance here. This is the marginal distance that I have, right? From here to here. I already told SVM considers the maximum marginal distance from the hyperplane, right? This has very shortest. So I'll tell, man, you've come up with a model, but still I feel this is very short. Let's try with the other model. Okay. So basically SVMs, they considered support vectors creating the parallel planes to make sure that the distance between those planes are maximum. The margin value is high. This is what SVM normally checks for. Okay. You're clear about this? Why didn't I take another hyperplane like this?
yes, ma'am.
Okay. Yeah. So let's go ahead. I'm clearing it. Okay, let's go ahead and see, okay, what are these positives? What are negatives? How do I come up with those solutions? Okay. So SVMs, the main idea is split the input data into the most optimal way. True, we are doing that, split the data into the most optimal way. And the goal of the SVM, we already have told, obtain the maximum separating hyperplane. That is the maximum, the margin. Have a margin which is more. So separating hyperplane, I need to have it maximum. Yes. There are really two types of data over here. One is your linear, the non-linear data. The example that I'm showing over here above is the linear data, because when I draw a line, the hyperplane, I have two different classifications. I mean, two different groups that I can classify them into. Whereas I have a non-linear separable data. Example, what is that non-linear separable data? This forms my non-linear separable data. You can see here, I have few red points and I have few blue points. And they're telling me, okay, I'm giving you this, it's a two-dimensional space of X and Y given to you. Go ahead with identifying, go ahead with classifying it using your same SVM classifiers, or you consider your logistic regression or something, okay? Now I'll tell, okay, I have to draw a line. Suppose I draw a line. Now I have this line, I've drawn a line, okay? When I draw this line, is it separating or is it classifying the data points correctly?
Yeah, I think not exactly.
Why?
Well, if it was SVM, it won't classify properly, and plus the data points is actually segregated in a circular manner, so you can't
Mm.
differentiate which is which.
Exactly. So it is telling me that there could be a chances of one of the data point, one color of the data point lying on the either sides of the line, right? So when I tell red points, maybe there could be some of the red points over here. So obviously, when I try to classify such a model using the linear regression line, I will get an accuracy which is below than 50%. That is for sure. Okay. So in order to do this, there is a concept called as kernel trick. SVM kernel trick, okay, which basically it converts a two-dimensional space. Now this is a two-dimensional feature space that I have. So it converts this two-dimensional feature space into a three-dimensional or a higher dimensional feature space. Whenever you convert something like this from a lower dimensional to the higher dimensional, there are more chances, or the most probable way is that they get linearly separable, the three-dimensional or in the higher dimensional. Most of the time it is three-dimensional. Okay, when you put it into the higher dimensional, that is a three-dimensional way from 2D to 3D, the non-separable data becomes to be a linear data. So non-linear data becomes a linear data like this shown in the figure. When we do it practically, there are more chances of this getting like this. So I have a three-dimensional data where I plot the red points and the blue points, okay? When I look at this, obviously, can't I separate this when there is something separated data points? So I can draw. So what I can do is using SVM, I can draw the marginal space. I can draw a hyperplane where it connects, let me consider that it connects this support vectors and this below support vectors, and it creates a point with respect to the hyperplane. So I'll have my margin that I'm going to create over here. So few other points, a linear and non-linear data. A linear data, we saw the above example how we can do it, whereas a non-linear data, we go ahead. The non-linear separable data, we go ahead using kernel tricks, okay, the SVM kernel trick, where it converts from a two-dimensional space into a three-dimensional space, and upon that we can create this. So how does it work? This is what I have given a description about how algorithm SVM works, is that it uses the nonlinear data mapping to transform the original training data into a higher dimension from 2D to 3D. It transforms from the original training data, whatever the data training data that I have with respect to the two-dimensional, I convert it into a higher dimensional. With this new high dimension, it searches for the linear optimal searching hyperplane. It searches for, as I told you, SVM comes up with a optimal hyperplane. So it comes up with an optimal hyperplane like this, where it starts identifying or makes a decision, okay, which point belongs to which category. So a decision boundary that separates between the classes. And the input data can be classified into separate classes with the help of hyperplane. Now, so with the help of that hyperplane, I can easily classify it, and it is most dependent on the support vectors, because based on the support vectors is what I consider. Okay. So from the beginning now we saw what is an hyperplane, what are the support vectors. We also saw what are the margins, and after that the linear and the non-linear separable data. So till here, is there any questions? Because I'll be going ahead with the math derivations, which is quite very interesting for us to understand. Any doubts here till here? I'll go ahead.
Yes, ma'am.
Okay. So what is a math intuition over here? Okay, so the math intuitions here is, okay, in the left hand side there's one figure that I've written, in the right hand side there's one figure that I've written. Let me consider the left hand side of the figure first. Okay, so the left hand side I have some red pixels, the red data points, and I have some blue data points present here. Okay, so the red data points and the blue data points, which actually tries to separate our data. Okay, so now what happens, this is an intuition of the data points given to us. Okay, let's consider this is our data points given to us. Let's go ahead with a practical example of how this could happen. Okay, so now the practical example here is I'm taking this x1 and x2 is my coordinate space. Okay, x1 and x2, but I'm going to draw a line. Okay, this is my line. I'm going to draw a line. This is my hyperplane. Okay, my hyperplane where my slope is -1. I'm taking in the opposite direction because slopes, they have directions. So when I consider the line y is equal to mx plus c, I can represent the same line y is equal to mx plus c like this, or y is equal to w to the power of x, w transpose x plus b. I can differentiate the same. These are the representations of the line. So now when I have this, I know the slope of it, and I know it is passing through the origin. So my b is equal to 0. Okay, and I know I'm having two data points that I'm giving over here. One data point is -4, 0, and the other data point that I'm going to give is 4, 4. So I have two data points that I'm going to give here. Okay, now what I do from here is I have to identify, okay, how am I going to classify this? How does a value positive, how does a value negative come to a data point? Okay, let's see that. Let's calculate the value of y, because y is equal to mx plus c that I'm going to cover. Okay, let's calculate it. I know the value of m is -1, the value of slope is -1, and I know the value of b is also 0. The value of c or b is 0 because it passes through 0. Okay, y transpose, that is y is equal to w transpose x plus b. Okay, we're already 0, I'm writing it directly as 0. Now what I'm going to take is the w transpose, basically the weights that I'm going to consider right now is m and c. The coefficient values here is m and c. And I want to write it in the matrix format so that I'll be doing a matrix multiplication because I have the points as well. -4 and 0 is my point data point. So I'm going to write -1. So the value of m and the value of c, I'm going to write it over here. W transpose -1 and 0, m and c value. And the x value over here is, since I'm taking the first point over here, I'm writing it as -4 and 0. When I do a cross multiplication, I'll get minus and minus is going to be a +4. So I have a +4, which means it's a positive value. This is a positive value. So what I can state out is, if I try multiple times like this, I'll take one more data point here, I'll take one more data point here, I'll take one more data point here. When I perform like this, all of them will be positive values because the data point is below the line. If it was like this, we saw in the previous example, I had it like this. Any data point which is above the line is always going to be positive. Below the line is always going to be negative. We saw this in the linear regression line as well. Now I have something like this. So above this line is going to be negative, below the line is going to be positive. So which means that I'm going to write it like this. Any data point, suppose, which falls under this below line, all of them are going to be positive. I'll just try to analyze whatever I've read through to whatever I have. I'm just trying to analyze because I got a positive value. I'll write all of these data points that fall below the line is going to be negative, and all of the data points which falls above this line, okay, let me consider above this line is going to be negative. Why negative? Let's try out, okay. We have one more point here, 4 comma 4. Let's try out for that point. W transpose X, that is minus 1 and 0, okay. I have the slope of the line and the intercept B is equal to 0 into 4 cross 4. This is my data point 4 cross 4. When I multiply it, it becomes minus 4, which is a negative value. It falls under this. You can try any of the other samples also, you will get the value for that. Okay, so the intuition, now we got to know that when I have a line and the slope of the line, based on the slope of the line, I'll get to know whatever the data points that fall below the line, what data points will fall above the line, whether it is positive or negative. So till here, this is what the intuition of the diagram was. Okay, now I'll come up to this. So when I come here to the left hand side of the diagram, which tells me that, okay, this was my slope of the line. This was my slope of the line, okay, right? So I'm going to write, it is telling it has a value B because it is not intersecting at the origin. It is not passing through the origin. So there should be some B value for that. Okay. And I know this is y is equal to mx plus c, or w to the power of x plus b is equal to 0. Okay. I will write this as my first equation for this line. I've created a hyperplane, and for that hyperplane, I have this is the equation of that hyperplane. Okay. Now next, what does SVM classification do? When it is creating its hyperplane, it will consider its support vectors and it will create a parallel plane to the hyperplane, passing on the support vectors. Now, what we have to do next is identify the support vectors. So identifying the support vectors is the least distance with respect to the hyperplane forms my support vector. So I've got 2 over here. I have still many more. It's not that you need to have only one support vectors. You can have multiple support vectors. And normally, with respect to huge data sets, you will have a lot support vector points. Okay. So suppose I'm considering this right now, and what I do is I indicate the distance between this point to this point as x1, this point to this point as x2. So I have x1 and x2 that I'm going to indicate over here. Okay. Now for that particular line, what is the equation of that line? I have to get to know the equation of the line which is passing through that. So now I will write this. This is the parallel plane. Okay. This is the parallel plane. I'm just underlining it. I mean, dotted lines. I'm just placing a dotted lines for your reference in dark. Okay. So I have 2 parallel planes. So let's consider the first parallel plane. Okay. With respect to the x1 distance. Now, this is my x1 distance. Right. Distance of this particular thing. When I'm writing this, how should I write it? Because it's the equation of the line for sure. It's a parallel line to the hyperplane. So obviously it is also a line. I'll write W transpose of X plus B is equal to minus 1. One more point which I wanted to let you know is, since everything is positive or negative about the planes, rather than writing it as positive or negative, okay, we can term that telling to be with respect to ones like minus 1 and plus 1. Okay, differentiating telling that rather than negative point and positive point, it falls under the category of minus 1 and plus 1. I can immediately tell true or false. Okay, so minus 1 or plus 1. So I'm writing here because this is above the parallel line. Okay, this is above the parallel line as well as the hyperplane. So all of these values are negative 1. All of these values will be positive 1. Equation of the line also, I'm writing it as W transpose of X plus B is equal to minus 1 for this. Since it's going to be plus 1 for this, I'm going to write it as plus 1. W transpose of X plus B is equal to plus 1 and minus 1. Now I've got all of these equations, the line equations for all 3. So now this is my margin. Okay. How do I identify the margin next? From the intuition, we created a hyperplane. From the hyperplane, how did we get to know whether the points, that is the blue points or the red points, whether they belong to a positive category or negative category? We saw that. From there, we termed terminology telling that, okay, it belongs to the minus 1 or plus 1 category. From there, we identified, okay, we have given the equations of the, now we have all the 3 lines. We have given the equations of those lines based on the support vectors. So we have seen all of these things till now. Now what I have to do is, how do I identify the margin? How do I get to know? I have to tell, okay, if the margin is high, consider that. If the margin is low, no, you can go ahead with another optimal solution. How am I measuring that margin? How do I get those margin measurements? Okay. So the next, I'll just clear this for the following. Excuse me. So this is similar to that of the plane that we had, the hyperplane, and the two parallel planes, and the distance between x1 and x2. Okay, x1 and x2, I have it everything a simpler. Okay, I have these data points here and the data points on the above. Now what I'm doing, I have to calculate the x1, the distance, because when I tell, okay, I want the maximum margin to be considered, I have to know what is that distance, right? So what I'll do is I'll consider this to be as a two-dimensional space. Okay, from the two-dimensional space, I will be considering it, telling that, okay, I have to get x1, x2 minus of x1. This data point, if I get to know the distances between the data points, it is more well for me. Okay, support vectors. So this is one of the support vector. This is one of the support vector. Okay, and I know based on the support vectors, maybe even if the support vector is here, I do not mind. Okay, but I'll get to know the distance between x2 and x1. I'll have those distances, right? I have to get to know, okay, what is the distance that? So what I'll do here is I will write x2 minus of x1 basically will give me my distance. Okay, the marginal distance between that. So now what I'll do is I know the equation of this. I know the equation of this line. I know the equation of this line as well. All the three equations of the parallel lines, I know it. Now hyperplane and the two parallel lines. Now what I'll do, I'll take the two parallel lines. W transpose of x2 plus b is equal to 1. Why 1 over here?
It's below the hyperplane, so it's positive.
Yes, it's below the hyperplane, and since this is our hyperplane, or okay, for x2, okay, it's gonna be plus 1, and for x1 it's above the plane. Okay, so it's above the plane over here, so it's gonna be minus 1, and I have to minus it. So when I have to minus it, I'll have all three minus signs, so then this will get cancelled. Okay, so then this becomes W transpose. I take the common of it, x2 minus of x1, and this, since it's a plus, and it's a minus here and a minus here, this minus and minus will become plus, so it's going to be 2. So 2. Okay, and normally in your mathematical theory, the slope and the intercept, right, if you want to eliminate that, it is basically you can eliminate by using the norm function. Okay, where you add it on to both the sides of the equation. Okay, so what we do is, what is that norm? It's nothing but to remove the W transpose. We take the norm of it because it has a directional concept involved, the slope, which direction it is tending towards. Okay, so that's why we take the norm of it. Okay, which is two straight lines with W in between. Okay, so W transpose of X, so I'm going to divide this by here, again going to divide this by here. So now this term actually is negligible. You may need not consider it. Okay, but this is how your x2 minus of x1 is going to be 2 divided by modulus of W. This forms your optimization function, which is nothing but the measure of the margin. Okay, once your SVM, you really have to visualize all of these things. When you visualize, it is very, very helpful to understand. Can someone mute it, please? Okay, so you'll be able to visualize this more when you get to know, okay, suppose I have these data points and I'm going to draw a line between these. I have to identify the maximum of it. How do I get the maximum of it? I have to take the distances between these two. To take the distances between these two, this will be my optimization function, which is 2 divided by modulus of W. I'm going to take the maximum out of it, the optimization value. Okay, so finally, when I have to tell, okay, how does the SVM work? Okay, I have to tell that I'm going to update the slopes and the intercept values. Okay, such that, okay, I'm going to consider the maximum of, because I'm going to optimize only when how do I tell SVM works well? SVM works well when it has this maximization, margin values maximum. Whenever I consider that, I can at least tell that, okay, SVM is quite correctly implemented onto it. So to get that, I have to get max of 2 by W bar, that is this one, modulus of W. This is my optimization function. The value of it, x2 minus x1 is nothing but the margin. When I get the maximum value of it is what I'm considering. I'm going to consider that such that, how am I going to consider it? Any data point called as yi, any data point it can be, it's going to be 1. The value of it will be 1 only when it lies above the line or below the, it's based on the positivity m, whether it is this way or this way. The value of the point is going to be 1. If it is, the slope is in the positive way, then the value of the line is going to be positive only when it has all these data points in the positive side. It's above the line. So I'm going to just write it as greater than or equal to 1. This should be there. Else, the data point is going to be -1 on the other side of it. It is less than or equal to 1. I'm going to write these slope equations. This is very, very important. If I have to identify the marginal distances, I have to know where my data point lies, whether it is a positive side or the negative side of the line. So I'll be getting to know what is positive, what is negative with respect to this equation. Till here is basically how my SVM is applied. Next is how it is actually going to classify. SVM applied in the sense, how do I get the marginal distances between the two hyperplanes, between the two parallel hyperplanes and the center hyperplane? What is the marginal distances based on the support vectors? This is how I will get using this following equation. Identify the maximum distance. Based on that, I will check out where each and every point lies, and to those points, I'll give a value -1 or +1. Okay. How is it classifying? I have to think over, okay, I know where the data point lies. I know the marginal distances. How is it going to next classify? The next classification is done by using the second equation over here, which is one of the very important equation. We have seen the same equations in the logistic regression with case 1, case 2 and case 3. I would request each and every one of you to revise the concept of logistic regression with this case 1, case 2, case 3. Where exactly the point lies, how are we going to classify it based on the positivity or the negativity? So this is how we actually did it in the logistic regression by multiplying y into wt transpose into x. A similar equation, I'm writing it here, yi, any data point. It can be any, a positive point or a negative point, any data point with its w transpose of xi. This w transpose of xi plus b is basically the line. When I'm multiplying with the parallel lines, okay, all of the values should be greater than or equal to 1. It should be positive all time. When it is positive all time, we tell it is correct classification. If I get a negative value, it is a misclassification. Please, there is two differences over here, positive and negative with respect to the data point, only that is till here. Till here, whatever we discussed was, when I tell positive, it is below the line if the slope is like this. If I tell negative, it is above, the data point is above the line. These were all the discussions that we did. But the next step that I'm talking about, the positive negative, is the final classification. Final classification. So if I tell, okay, suppose let me consider, I take a data point over here. This is my data point. For that data point, what I do over here is, let me consider the yi of it is -1 because it's above the line, okay? It's going to be -1. And the distance, the transpose of the line is also going to be -1. Okay? So into -1, minus into minus, I will get +1. So I mean, I'm telling it's positive, okay? Positive in the sense, the data point that I considered above the line is classified correctly with respect to this. The similar, if I take a data point here and I classify this, and even for this also I have to get positive. When I get something like that, I will tell it is correctly classified. But imagine we had a case 3 problem, okay? Rather than a blue point, I had a red point. All my red is here, but I had a red classification in the other side of it, okay? And when I do this, the value of this was supposed to be, but I'm still considering this to be as positive. Positive value of this into the negative of the slope is -1. Positive and negative is negative, obviously, which means it is telling you have wrong classified, you have misclassified the classification. It has to be here, but it